going to say 3x squared minus 4x and plus 4. And I'm going to choose a decent interval that starts at 0. Because if we want to be not decent, we will start at any other number and it will get more complicated. So I'm going to start. We can also illustrate with any other interval. Of course, you can choose the interval. Let's say 0 to 4. Okay. So the question, let's write the question first of all, so we know what this is. Find the area under f of x on 0, 4 using the limit of the Riemann sum, and also check with, this is a k here, with the definite integral. I'm going to do this first because this is the easiest thing to do. Doesn't matter the order. You choose the order. It's up to you. As long as both are there, it doesn't matter. So 3x to the third over 3 minus 4x squared over 2 and plus 4x. And we simplify. And of course, from 0 to 4, luckily I only have to plug in 4. And this is 64 minus 16 times 2 and plus 16. So this is 64 minus 16, right? And I think that this is 48. So I'm expecting an answer of 48. I cannot fudge it. I'm not going to, create any or fabricate any step or calculations, but this is what I expect to get. Good. So then I show the limit as n approaches infinity from the sum from I equals 1 through n from delta x f of x I. This is what the problem is asking me. So if, let's say, if the problem is worth 10 points, this will be 8 points and this will be 2 points. So this is a very important part. Why this is also important is because you're going to see a lot of this in Calc 2, the summation notation, a lot in series. So this is also a good practice. I cannot start this. This doesn't mean anything to me at this point. I have 3 preps. If I don't get the preps yet and simplify everything, I will not start the limit. Okay? So if you remember the 3 steps, the three preps are, first of all, I have delta x. By definition, so remember, we have here 0, 4. This is a comma b, actually. So delta x is b minus a over n. 4 minus 0 over n, which is 4 over n. So this is done with the first prep. The second prep, this is the interval 0 to 4. And I want you to remember how to determine the xi. The xi is determined as 0 plus I delta x. If I have here 5 or 10 or negative 3, I will have negative 3 plus I delta x. So I have 0 here. That's why I write 0 plus I delta x. But I have delta x. So this is simply 4I over n. So xi is 4I over n. Prep number 3 on the next page is f of xi, this. So this is prep number 1. Inside here is prep number 3, number 2, and this is prep number 3. 1, 2, inside 3, the function. So, which page am I on? 7. So I want to find f of xi. So this is number 3. The function, I have it right there. So this is f of 4i over n. F of xi, which is 4i over n, f of 4i over n. So this is 3 times 4i over n squared minus 4 times 4i over n plus 4. So let's take a moment and see if you have any questions on this. Is this okay so far? Please say something so I know how to if to continue or if you have questions. Is that a yes? Is that a no? Is anyone with me? Okay, I got a yes. Okay, so now I continue simplifying it. So 4 squared, 16, times 3, 64. I squared over n squared minus 16i over n and plus 4. So one more time. Is 16 times 3 okay? Is that 60? Oh! See? I wasn't thinking. So 48 I squared over n squared minus. Very easy to make a mistake in this. So 16i, no excuse, no excuse. So 16i over n plus 4. Okay, now I can start the limit because I have all the preps I need. So then the area equals limit as n approaches infinity from the sum from I equals 1 through n, delta x, 4 over n times this. Okay. Remember what we did. If you did not watch those videos, please do that. I have to move this constant in front, and then the sum of the first term plus the sum of the second term plus the sum of the third term. So I write limit as n approaches infinity, 4 over n outside. So the sum of this, 48i squared over n squared minus the sum of 16i over n plus the sum of 4. Of course, they're all from I equals 1 through n. Like I did with this constant, because it's a factor, I have to do the same thing with these. This is a constant, which is a factor. It will go in front. This is a constant, does not depend on I. It will go in front. This is a constant, and what is left here is 1. 4 times 1. So I copy limit as n approaches infinity, 4 over n. 48 over n squared, the sum of I squared, minus 16 over n, the sum of I, plus 4, the sum of 1. Of course, from I equals 1 through n, I equals 1 through n, I equals 1 through n. Now all these will be replaced. This one is replaced by n. This one is replaced by n plus 1 over 2. N plus 1 over 2. And this one by n plus 1, 2n plus 1 over 6. And I continue. Any questions? Let's take a moment. Any questions so far? Is this okay?
Yes. Yep.
Okay. Good. Moving on. So limit as n approaches infinity from 4 over n. 48 over n squared. I'm going to multiply these two. It's always easier if I already do it here. 2n squared plus 3n plus 1. This and this. Divided by 6. Minus 16 over n. Don't multiply these, just for this one. And plus 4n. At this point, all the summation notations are gone. That's all I needed for now. So now let's see if we can simplify. An n with an n. A 2 here and 8. So therefore, I have limit n approaches infinity, 4 over n. And as you see, the least common denominator will be n. Now I have to distribute 8 in here, so I have 16n squared plus 24n and plus 8. And then we have the least common denominator is still n, so negative 8n squared and negative 8n. So 8 times n, but with minus in front, and 8 times n times 1 with minus in front. This one is over 1, so it needs an n. So plus 4n squared. Finally, almost, n approaches infinity. The denominator is n squared. 4 can stay and wait patiently, or we can put it in front. Why not? Let's not even worry about it. This is true for integration, is true for differentiation, is true for limits. You can wait outside patiently. So wait patiently. Good. So 16 plus 4 is 20. 20 minus 8 is 12. 24 minus 8 plus 16 and plus 8. In order to determine this limit, I know L'Hopital's rule, infinity over infinity. I will differentiate. So for limit as n approaches infinity, 24n plus 16 divided by 2n. Again, infinity over infinity. Limit as n approaches infinity. Remember, the limit does not go away. 24 divided by 2. I differentiate the top, I get 24. I differentiate the denominator, so this is 12. So 4 times 12, it better be 48, because then it will be embarrassing for me to start this from scratch again. Okay, this is a lot of calculations. I don't recommend, if you see that you made an error, I recommend start from scratch. Don't try to, in all this gibberish, try to find the error. It's very difficult. Not impossible, but difficult. So you will have an example in which you have to show your algebra skills. You have to show that you know how to manipulate this summation notation, and you have all these clear, and you do the algebra correctly. The books had a slightly different method. If you like the method in the book, please use it. I don't have anything against it. I think that this is clean, but if you have other shortcuts or that work, I'm fine. So this is finding the exact area under a graph using the limit of the Riemann sum. Do you think we need another? We had like at least 2 or 3 done. This is probably the 4th, but it doesn't matter to me, whatever you need. So here's a list of what to expect for test 4. So from 4.9, obviously antiderivatives. I always hope that you look at the videos, but also at the solutions for homework, right? I always post solutions before I start grading or your homework. So the antiderivatives. And then in chapter 5, of course, definite and indefinite with substitution or not. What we talked about here, the limit of the Riemann sum. What else? The net change theorem. Properties of definite integrals. Differentiating a function given as an integral. I can't think, I'm flipping through the book right this moment to see if I forgot anything. Oh, yes. Approximations of areas using leftmost point, rightmost point, and midpoint. Using leftmost point, rightmost point, and midpoint. Not more than 4 subintervals. No, that's not going to be a torture. Top 4. Okay. So the definite approximations, limit of the Riemann sum, properties, we said that. Yes. Fundamental theorem of calculus, yes, part 1 and part 2. This is part 1. And part 2 we know because they're here in definite, the definite integral. There is nothing else. And the net change theorem and the substitution. That's it. So far we did this and this. What would you like to continue with? Or maybe you have any questions.